live. There are many people who can take for some time. Good afternoon. I hope, I don't know whether how many of you would have gone back and looked at whatever we studied in the previous lecture. But I hope, and anyway, this part is a relatively easier one. So it is fine. I'm not able to maneuver the slides. Okay, so just a very brief, before I start, any specific question from the last class's portion? If there is any, you may write in the chat box. And what we'll do is in next 1.5 hours, we'll take 3 to 4 breaks, small breaks. And you can keep typing your questions in the chat box and let's try to solve them if there is any query or any difficulty. So I hope I'm clear. So in last class, we studied about what is unit cell, how do we define unit cell, what are different crystal system, what are different lattice types, and also the concept of basis and how do we count the number of atoms in the unit cell. We also talked about what are Bravais lattice, how many Bravais lattices are formed, and how actually basically does the term Bravais lattice come into picture and what exactly is its meaning. Okay, so what we'll start with today is again simple concepts, but of course the most indispensable concept for somebody who does solid state chemistry is concept of lattice planes. Okay, so again, when somebody tells you that there are planes in the unit cell or in the crystal structure, let's be very clear about it. The crystal structure doesn't really know that it has planes, right? So it is a concept that is based on unit cell shape and size. So what you do is, in fact, for your convenience, you devise this concept of lattice plane so that you can actually assign the atoms to the lattice plane. And then you can build the crystal structure according to it. So that kind of eases out how to view the structure. So of course, every lattice plane has got a set associated with it. And the lattice planes are characterized by the interplanar spacing D. Okay. So a set of lattice planes will have a fixed interplanar spacing D, which is of course fixed for each set of lattice planes. I'll just describe that. And how do we label it? We have to, kind of identify them. When we invoke this concept, we also have to be able to identify them. And they are characterized by a set of 3 numbers, which are called HKL, which are also known as Miller indices. Okay, so nothing to be confused about. What Miller indices basically say how your plane is intersecting the 3 main crystallographic axes, which are X, Y, and Z. Okay, so how do we determine the Miller indices of a plane? So again, a very simple thing. I'm really sure all of you would have, most of you would have done it, but let's kind of give it a quick revision. So you consider this is your unit cell. Okay. So consider a cube of side A, okay? And this is how it is interacting the simple. Consider a cube of side A. A is equal to B is equal to C. So all of them are A because it is a cubic unit. Now, how do I determine the Miller indices of the plane? Now, suppose I am considering the plane which is shaded in this figure. Okay, if you can see, can I get a mouse so that at least I can use the cursor? Okay, so they are able to see the cursor. No?
Yeah.
Okay, so consider this, and suppose I am considering this particular plane. How do I calculate the Miller indices of this plane? Simply, you first consider what are the intersects this plane is making on your x, y, and z axis. So if I consider this as x, this as y, and this as z, it is making an intercept of 1. Okay, because it is actually making an intercept of A, but A is let's say 1. Then it is making an intercept of 0 on y-axis because it never intersects y-axis. This is parallel to y-axis. Also, it is parallel to z-axis. So it makes, I'm really sorry, it doesn't make an intercept of 0. It makes an intercept of infinity because it is not intersecting y or z-axis. So an intercept of 1 on x-axis, infinity on y and z axis. So you have a infinity infinity, or I'll make it 1 infinity infinity. Now, what you do next is you take the reciprocal of these intercepts, which will be 1 by 1 by infinity, and 1 by infinity, which will make it 1, 0, 0. Okay. So Miller indices of the plane shown here is 1, 0, 0. Actually, as you learn more and more about solid state chemistry, about crystals, about structure, rather than just fixating on the numbers that we are talking about, you should be able to see through what the thing is trying to tell you. And this actually would be my aim of taking you through this general materials chemistry course. So if ever you see something like 100, okay, now Miller indices, what it says is it is a plane that is making an intercept of this, and this number on x, y, and z axis. You need this. Okay. So what it actually means is if it is showing an indices of 0, means it is parallel to that particular plane. So immediately it should click to you. It is a plane, okay, which is on x-axis making an intercept of what is the lattice parameter on x-axis, that is a, equal to that. So that is 1a. 0 means it is parallel to y-axis. 0 means it is parallel to z-axis. So immediately this plane should flash in front of your eyes. Now similarly, if I say if it is 0, 1, 0, again very simple. 0, 1, 0 means it would be this plane. Okay. The one that makes an intercept of 1 on y-axis but is parallel to x and z-axis. Similar is the case of 0, 0, 1. Now, when I say 1, 1 means intercept of lattice parameter corresponding to that axis, which is A on x, B on y, C on z. If it is Q, then all A is equal to B is equal to C. So the ones here are all same. I mean, the meaning of 1 is same, which again means that if you have a cubic system, if you come to this particular statement, if you have a cubic system, basically your 100, 010, 001, they are equivalent because all of them are making an intercept of a lattice parameter on the corresponding axis parallel to the two axes, but also that intercept on different axes is equal because it is a cubic system. A is equal to B is equal to C. And they are said to be belong to family of planes. Okay. So when again, I just kind of forgot to tell you that when you denote the Miller indices, they are denoted without any comma and in small bracket, the way it is shown here. And when you are trying to denote the family of planes, then you denote it like this with a curly bracket without any comma. Okay, now sometimes you encounter a negative Miller indices, that is -100, which is denoted by bar. So 1 bar 00. Now, what is the meaning of negative Miller indices? Nothing, very simple. It's just that if you are considering this as the origin, then you are making an intercept of 1 here. If you're talking of -1 means you go back on x-axis, okay? Which means now the plane is behind your origin. So it is as simple as that. So you can have negative Miller indices and it has a very simple meaning too. And as I just said, instead of plane, it's also got a specific interplanar spacing that is denoted by D. So just solving one or two planes indices with you to make this concept even more clear. Look at this plane, which is they are able to see the cursor, right? Okay, which is colored in blue. Now, if you work out with me, let's write X, Y, Z on ABC. What is the intercept that it is making? On X-axis, 1. On Y-axis, 1, but it is parallel to C-axis, so infinity. Clear? 1, 1, infinity. Okay. Now, if you take the reciprocal of this, because second step is you have to take the reciprocal. So 1 by 1, 1 by 1, 1 by infinity, which makes it 1, 1, 0. And reduction means sometimes you might get a fraction. In that case, you have to multiply that fraction, or if you have more than two fractions, take an LCM, multiply by that. That is called reduction. You have to make it a whole number, and then the Miller indices of this particular plane is 1, 1, 0. Okay. Again, even without drawing, you should be able to say 1 means intercept of 1 on x-axis. 1 intercept of 1 on y-axis. 0 means it is parallel to c-axis. Coming to the second one. Now, if you see this plane on x-axis makes an intercept of half. On B, parallel to B and parallel to C. That means infinity, infinity on y and z. Take the reciprocal, you have 2, 0, 0. Reduction 2, 0, 0. Miller indices are 2, 0, 0. Now, there's one interesting point I want to tell you here. Did you notice that this plane was 1, 0, 0 and this plane is 2, 0, 0. The 1, 0, 0 was farther from the origin, while this one is half the distance. That means closer the plane is to origin, higher will be the numerical value of Miller indices. And let me again put a very interesting point forth, which obviously we study, but we don't really think it through. And this is how our concepts get clear. How many 100 plane would be there in the unit cell? Only one, okay? Because it is the maximum intercept, right? But how many 200 planes would be there? Double. So one at this, and because its D is half from the origin, at another half, this also would be 200, but this is also 100, okay? That means there are twice the number of 200 plane in the unit cell as compared to 100. On the same line, there are thrice the number of 300 plane in the unit cell as compared to 100. And 100, 200, and 300, they are all parallel. Okay. So I hope I'm making sense to you. Okay, now this of course we have done on the previous slide. Just take a minute, okay, and try to do this. Or anyway, this presentation would be shared with you, I'm sure, by tonight or tomorrow. What I want is in the next class, I would want you to tell me the Miller indices of this plane. Okay, that's just a small assignment. Will take you a minute, but it'll be good to start next class with this. All right. Okay. Now, Miller indices for directions. The way we have planes, we also have directions, because when we talk of crystal structure, we talk about planes, we talk about the atoms occupying the planes, and we also talk about the directions in the crystals. Okay. So, of course, now we have to denote the direction also, because we cannot really say south, east, north, and west, right? So, how are directions? We have to quantify them. So, directions are also quantified by Miller indices. Okay, so let's say, so basically what you do is, suppose you had to determine this direction. You simply have to draw a parallel line to whatever direction you want to determine, the parallel line to that direction, but passing through origin. Okay, let's say we wanted to determine for this line, and I've drawn OA, which is parallel to my desired line. Now what you do is you simply find what is the intercept it makes on x, y, and z axis. So let's say here, obviously this is a 2D thing, so z is 0 and it is making an intercept of 1 and 1. So now you don't really have to take any reciprocal, just that if it is a fraction, make it a whole number. So direction OA is 1, 1, 0. Difference, when you indicate the Miller indices of plane, it comes in the small bracket. When you indicate the Miller indices for direction, it comes in the square bracket. When you indicate the family of planes, it is a curly bracket. When you indicate the family of direction, it is this kind of triangular bracket. Okay, let's solve another one. Now, suppose I want to find what are the Miller indices of direction OB. Okay, so again, we see that it passes through the origin. Then what is the intercept it is making on x, y, and z? An intercept of let's say 1 on x-axis and 2 by 5 on y-axis. Okay, so this is x-axis, here it is 1 and here it is 2 by 5. So what you do, it is basically 1, 2 by 5, 0. Now take the LCM, 5 multiply 5, this 1, 2 by 5, 0 becomes 5, 2, 0. Okay, so that is how we find the directions in the Miller indices. Now, these are some of the important directions in the crystal. And one more interesting thing I've not mentioned here, but I would want to tell you, if your plane and direction have got same Miller indices. Okay, you remember what your 100 plane was? This was your 100 plane, right? And a 100 direction would be the direction perpendicular to this plane. So this was your 100 plane and this is your 100 direction. Okay. So just sit and think through it for 2 minutes. And these situations, what as a solid state chemist, as a material chemist, I would want you to be able to visualize things, no? Not cramming it or, just cramming and then reproducing. These are the things that you visualize and these are very, very logical things. So they're easy. Of course, it might take some time, but they're good. If you can visualize it, the life becomes relatively very simple in that case. Okay, so here we kind of end with some terms that we use in solid state chemistry. Now, the next lecture, or let's say probably, I hope to finish it today, but let's see. We'll talk about the crystal chemistry. Now, there are two terms that you encounter in this context. One is crystal chemistry and other is crystallography. Okay. So what is the difference between the two? Crystallography, let me first tell you this, because this is what Dr. Kanubari will take for you in the next module of the course. Crystallography refers to experimental methods that you can use to determine the structure. Okay. And what are those experimental methods? X-ray diffraction, neutron diffraction, electron diffraction, then powder XRD, single crystal XRD. Those constitute crystallography. And what is crystal chemistry? Crystal chemistry is basically, it teaches you how to describe a structure, how to classify the structure, what are the factors that could affect your structure, what is the relation between the structure and property, because that is the whole aim of studying the structure. See, what is the point in studying one is cubic, one is tetragonal and all that? The only thing is you want to have a practical application of your knowledge. What we are looking at, good properties, good functional materials. And the properties ultimately depend upon what is the crystal structure of your material. Of course, it depends upon chemical bonding and everything, but all of these are interrelated. And crystal structure constitute one of the most important factors that bring out a property in your material. So crystal chemistry also tells you what is the relation between the structure and physical or chemical property. Also, because sometimes, you're looking at one material and it undergoes phase transition, but at some point, but one of the phases of that material does not have that property that you're looking for, but the other one has. So you want to create the condition where you can stabilize only the material that is desired, that has a desired property. So crystal chemistry also tells you about the conditions under which a particular crystal structure is stable, so that you can work out around it to get that stable structure. So I hope this is okay. And now we move on to how to define our crystal structure. Okay. Now there are three ways by which you can understand. Ultimately, all of them lead to the same thing. It's only how I want to understand and look at my structure. One way is you define, because we discussed in last class that unit cell is the smallest entity that can actually replicate your crystal structure in 3 dimensions, right? So one thing is that we define the unit cell. Okay. That is, what is the shape of the cell, size of the cell, what are the positions of atom. Because once you know how the unit cell looks like, you effectively know how the crystal structure looks like. Now there are two other ways, you know. The unit cell tells you only the small entity. There is one way, closed packed structure, which means how your atoms or ions are packed in 3 dimensions. And other one is space filling polyhedra. Because all of you know your atoms are coordinated, cations are coordinated to anions are coordinated to cation. So depending on the coordination, they adopt some kind of polyhedra, tetrahedra, octahedra, or sometimes we have, you know, a little more complicated trigonal bipyramids and so on. So how does they exist? In form of what is the polyhedra? Basically, what is their coordination number? And how those polyhedra are linked together to create that structure. Closed pack structure and space filling polyhedra give you a better 3 dimensional views, and hence all the approaches have their own merits and demerits, and it's good to have an idea of all of them to see whatever suits you most. Okay. Now, when we talk of closed pack structure, now basically let's go a little bit into it. When we say close packing, basically it considers that all your metal atoms, ions, whatever you are considering, they are hard spheres, and you have to arrange them so that under those conditions you achieve maximum density. Okay. Now that is the biggest criteria. So what is, once you have achieved 2 dimensional packing, then consider the most efficient way of packing equal size sphere in 3 dimensions. Okay. Now let's just try to understand whatever I talked about. Let's say you have equal size sphere. If you want to arrange them so that they can have maximum density, this is how you will arrange them. This is the first line. Then in between the groove, you will place the second line, and then in between their groove, you will place the third line, and so on. Okay. So what is the closest neighbors in contact here? If you concentrate on any one atom, you can see that it is surrounded by 6 neighbors. Okay. So in 2 dimensional, whenever you want to have maximum density, the maximum coordination number you will get is 6. Now we have to place another layer of atoms on it. We are talking about crystal structures in 3 dimensions, isn't it? So what are the different kind of interstices present here? If you can see that there are these triangular interstices of 2 types. One pointing upward, the other pointing downward. The one that point upward, let me say, let us denote it by 1 for the ease of understanding later on. The one that points downward, let us denote by 2. Okay. Now let's see how the story unfolds. Now I have to place a second layer of identical spheres on. Let's say I place it on, I have the option. One thing you should understand is they're so close by that I cannot really put it on both 1 and 2. I have to choose one of them. So let me choose one. So I place the second layer of identical spheres on the interstices that are pointing upward. So I get something like this. Okay. Now your second layer will also have 2 options. The triangular interstice is either pointing upward or pointing downward. For the third layer, now you have option. Either you can place it on 1 or you can place it on 2. Now, if you carefully look at it, if you place it on 2, that is the one that is pointing downwards, okay, then you are placing the third layer exactly on the top of first layer. Okay. So what you are getting is, if you denote your first layer by A, second layer by B, third would be again A. So fourth would be again B. Okay. So what you get is an AB packing. This is a very famous word that we use for it, AB type packing. But in technical terms, this is called hexagonal close packing or HCP. Okay. Now, let's say my second layer, as I told you, we place it on the triangular interstices pointing upward. Now, suppose I place the third layer again on triangular interstices pointing upward. Now, your position of the third layer is neither similar to 1 nor similar to 2. It is third octave. And now if you again put it on interstices pointing 1, then you will repeat your repeat your arrangement of first layer. So what I'm trying to say is layer 1 is similar to layer 4. So you had A, B, C, and then A, B, C, and ABC, and this will what repeat infinitely, and this will give you what we call as cubic close packing or CCP. Please pardon the printing error, typo error here. This is cubic close packing or CCP. This is hexagonal packing or HCP. HCP is ABAB. CCP is ABC ABC. Okay. Now, coordination number in both HCP and CCP is 12. If you try to, I don't know if you can really imagine it or not. We said in one particular layer, let's assume this is a second layer. Okay. So it has 6 neighbors on top of it. Oh, sorry, in the same layer. Then, because you are filling only one kind of interstices, so there will be 3 neighbors in the layer above this. So 6 plus 3, 9. Now, if you go below it, again, because you will be filling only one type of interstices, either the ones pointing upward or the ones pointing downward, depending on HCP or CCP, it will again have 3 neighbors. So 6 in the same layer, 3 on the top, 3 below. That gives you the coordination number of 6 plus 3 plus 3, 12. Both HCP and CCP have got coordination number of 12, and the packing density, despite packing them so close, the maximum packing density that you can achieve is 74%. Okay, and how do we calculate it? We'll calculate this. I'll tell you a little while later when I tell you about the unit cell corresponding to HCP and CCP. Okay, so we'll take a break of 2 minutes and let me know what is not clear to you so far. Please type in the chat box or ask whatever you feel like. I would prefer you typing your comment in the chat so that we can address as many as possible. Okay, whatever is being taught, is it clear to you so far? At least type a yes so that I know that we are moving in the right direction. Okay, thank you. All right, great to know that. Let's take a minute's break. Think about anything that you've not understood so far, and then we'll move forward. You can put the video on. share. Okay. It's unmuted.
Oh, got a black box. Yeah.
Okay. So I'm not able to do your slides. Okay. So, as I said, any structure can be viewed in all the forms, whether as a unit cell form or the closed packing or the space filling polyhedra. We just talked about HCP and CCP. What are the unit cells of these two packing? Okay, now that is something that I'll tell you about. It could be a little tricky, but let's try to see if we can get into each other's wavelength and understand it. Okay. So hexagonal closed packing, this is the unit cell of HCP. But if you take it here, okay, now this is your layer A, this is your layer B, the one in the center, and this is your layer C. And this is how the smallest unit of the hexagonal closed packing look like. But the unit cell of HCP is not this big hexagon. If you take it, if you just join this, and then make a parallel pipe, that is the unit cell of the hexagonal closed packing. That means actually you can make 3 such parallel pipes here. I wish this stylus was working, but okay, so let's say you join this, and then you join this, and then you come down. Okay, something, it will look something like this. So these kind of 3 units are there in this particular hexagonal parallel pipe, and this is the unit cell of the hexagon, wherein you have 4 atoms at the corner. It is basically 1, 2, 3, and 4. Then 5, 6, 7, 8. These are the corner atom, and this one is in the center of it. Okay, so this is how your unit cell of HCP looks like. Now, because the other day we learned to count the number of atoms, right, in the unit cell. So how many atoms are there in this particular unit cell? The 8 in the corners, they contribute 1 by 8 each. So 1, right? 1 lattice point. The one in the center is completely contributing to this particular unit cell. So it is 1. So 1 from the corners and 1 in the center. That is 2 lattice points are there in the unit cell of hexagonal closed packing. Now, what is the coordinate of, because this thing also I want to talk to you about, because as we move to the crystal structures, I will not repeat these things again and again. Now, what are the coordinates of the lattice points? Okay. Now, assume this is your 0, 0, 0, the one at the back in the bottom plane, right? Because now, if this is 0, 0, 0, you can tell me that there are 8 lattice points. This is 0, 0, 0. So this is let's say 0, 1, 0. This is 1, 0, 0. No, it doesn't happen like that. Because what we said is, we discussed that the corner atoms, all of them together contribute 1 lattice point, because each one is contributing only 1 by 8. Plus, if you just think about it, each corner atom is the corner for some other unit cell also, because they're anyway combined together. So this is shared by 8. Okay. So when I say that there is a lattice point, there is an atom at the lattice point 0, 0, 0 in your unit cell, it should immediately tell you that all the 8 corners of the cell are occupied. All of them have one coordinate, that is 0, 0, 0, and they meet only one lattice point. I hope this is clear. So the coordinates of the lattice point of hexagonal unit cell One, now there are two lattice points, so we need to have two coordinates, right? One is 0, 0, 0, and the other one is this one. So what would be the coordinates of this? One thing is clear, that its y coordinate would be half, because we know that layer A, layer B, and layer C are equidistant, right? So if this is 0, if this layer is at 0, and this layer is at 1, this layer has to be at half. So Z coordinate is half. But if you make an impression of this lattice point on the XY plane, like let's say, hypothetically, you put a hand on this red ball and push it down to the bottom plane. It will occupy this position, okay? And this is, so if you can carefully see it, because it is ultimately lying, let's say if I consider this bottom layer, it is ultimately lying on the top of a triangular interstices. So it cannot occupy a middle position in this bottom plane. It is somewhere here, and now I will tell you that it makes an intercept. If you kind of join this, it is 1 by 3 here and 2 by 3 here. I hope this is clear. The coordinate of this lattice point is 1 by 3, 2 by 3, half. A unit cell of HCP, that means there are two lattice points in the unit cell of HCP with the coordinate 0, 0, 0 and 1 by 3, 2 by 3 half. Now, if I tell you that there is a structure which has a unit cell, it has the lattice points at 0, 0, 0 and 1 by 3, 2 by 3 half, immediately you should be able to draw a cube. Of course, this is not a complete cube because this angle is 120 degree, not 90 degree, with atoms at the corner and one atom at this coordinate. Okay, I hope that's clear for HCP. Now, what is the unit cell of the CCP? Okay, now it is a little trickier to understand, but let's see. First of all, let me tell you that the unit cell of CCP, that is cubic closed packing, is your face center. Okay, and when I say face center, we did it yesterday. The atoms at the corners and atoms at the center of all the 6 faces of the cube. How many lattice points are there in the unit cell of CCP now? One from the corner, okay? And because the face-centered atom contribute half to one cube, we discussed it very nicely yesterday. So half into 6 is 3. One from the corner, 3 from the faces. That means the unit cell of CCP, which is face-centered, has got 4 lattice points. And what are the coordinates of those lattice points? Let us just do that. The one at the corner, we just agreed because of the single lattice point. And let's consider this as the origin is 0, 0, 0. Okay, we agree on that. Then, okay, now, because the 6 faces are contributing 3 lattice points, each face is contributing half, 6 faces are contributing half into 6, 3, there have to be now 3 more coordinates. Okay, so what is those 3 more coordinates? Let us try to find the coordinate of this. What is this? It is making half on x-axis, half on y-axis, and 0 on z-axis. Half, half, 0. Good. Let's come to this. This is half on y-axis, half on x-axis, and 0 on, half on z, half on x, 0 on y. Half, 0, half. Okay. Then we come to this particular, which is now this is equivalent to this. This we have done. This is now this one. So this is half on x-axis, half on y-axis, and half on z-axis. Half, half. No, it cannot be. It will be half, half, 0. So you have 0, half, half. You have half, 0, half, and then you have half, half, 0. So 4 lattice points are in the FCC lattice are, or in the unit cell of a cubic closed packing are 0, 0, 0, half, half, 0, half, 0, half, half, 0, half, half. Okay. Now I want you to think about it. Why didn't you ask me what will happen to the remaining 3 lattice points? Now, see, we said 0 means the 0 of your A axis, B axis, or C axis. Okay. If you have defined something here, right? If you have defined this particular face is automatically defined because this is the bottom of this unit cell and this is the bottom of the second unit cell. That means if this is half 0, this is half 1. Okay. But for the unit cell on top of it, it is still half 0. Right? That is the reason. So everything actually converges. A face contribute half. That is why even though you can mark 6 points, there are only 3 lattice points because the other half is being contributed to other unit cell. If I include all the 6 in this unit cell, then this will become double the number of lattice points that I require for my structure. Okay, so I hope this is clear. I know if you're doing it for the first time, it might get a little this thing, but all these concepts are very easy to understand once you simply sit and read it for 5 minutes. Okay, so now I don't really expect that you will understand it immediately. We just talked about that the unit cell of cubic closed packing is face-centered cell. But how does it look like? Okay, now difference between HCP and CCP, the unit cell position was the unit cell of the HCP node, the basal plane. Basal plane is these flat planes. The basal plane of the unit cell of this HCP coincide with the closed packing layer. Okay, I hope you can see this. This was your A layer. This was your B layer. This is again your A layer. Okay, so the plane of the unit cell actually coincides with your A layer. But in case of CCP, that is why it is a little difficult to visualize. Now, it doesn't coincide with the closed path. The base of your cube, that is this base that you are seeing here, it doesn't coincide with the closed path layer. The closed path layer actually is along the 111 plane. So if you can imagine, your unit cell is kind of tilted in this way. Okay. Now you see this is layer A, all right. This is layer B, this is layer C, and this is again layer A. So this is how your unit cell is placed in it. This is the top face. These are the side faces. These are the back faces. And there somewhere this is the bottom face. I hope you can put your imagination to it because it's a nice thing to visualize. And if you're not able to do so, even that is fine. Okay, just go through it again and again, and this will definitely come to you. Okay, so this we just did. Packing of the layers, close pack layers in CCP coincide with the 111 plane of FCC unit cell. There are 4 atoms, 4 lattice point. I should not say atoms. This is wrong. Never say atom. 4 lattice point per unit cell. Of course, the lattice point could be atom. Lattice point could be empty spaces. But these are those lattice points which you repeat in 3 dimensions. You will get your crystal structure. All right. Again, I just attempted to get a different picture so that you can see it. Okay. So hexagonal, the basal plane coincide with the closed pack layer. This is your FCC, the unit cell, and these are your closed pack layer. And this is the 111 plane. So the closed pack layer actually coincide with the 111. I hope when you go through it again and again, you'll be able to kind of make out. Okay. Now, because we have to study the structure, right? And in CCP and HCP, whatever we talked about, these are only we are talking about same kind of atoms. Okay, hard spheres, but same kind. But ultimately, we have to go towards the ionic solids, studying about the crystal structure of them. And then we'll talk about, okay, this makes CCP, that goes in the tetrahedral hole, that goes in the octahedral hole. So in unit cell, now we have to imagine, we have to see where actually those tetrahedral and octahedral hole lie, both in terms of close packing as well as unit cell. So that, you know, the later part of the lecture becomes really easy for you to understand. Okay, now just think that green layer is layer 1. red layer or the orange layer is layer 2 or layer B. Now, whether it is HCP or CCP, layer AB will be remain same for both of them. It's only the third layer that makes the difference, right? Now, if you concentrate at this particular orange atom, okay, now this is at the, consider this as the tip, okay, and consider these three green spheres as the bottom. What is it? It's a tetrahedra. So whatever lies, the space that lies between this orange atom in the second layer and the three green atom in the bottom layer is a tetrahedral group. All right. Similarly, if you are able to imagine a layer below this green layer, let's say it could be a blue layer. There also, at this position, if this is an HCP, these three atoms, these three green atoms with the blue atom at the bottom will form another tetrahedral hole. So this is how tetrahedral holes are placed in the closed packing. And how do you have octahedral hole? What is an octahedra? If you can imagine it in two ways. A square with an atom at the top and an atom at the bottom. Or you can also imagine it as two triangles staggered to each other. Staggered means something like this. A triangle on the top, a triangle at the bottom. Six, and the place inside is symmetrical like an octahedra. Because this is the triangle on the top, this is the triangle on the bottom. This is the shape that you generally associate with an octahedra, a square, an atom at the top and an atom at the bottom. Okay. So basically what I just told you, which many of the students take little while to understand or to correlate, is what is octahedra? Nothing but a pair of parallel staggered triangles. Okay. So this is how your octahedral hole looks like. Concentrate on anything, concentrate on these three oxygen orange atoms and the green below them. The space between them, these are two staggered triangles, is an octahedral hole. Okay. So one thing that you have to remember is for every sphere, there is for every sphere that you have in your closed packing, there is one octahedral hole and two tetrahedral holes. That is, if your closed packing is made up of n balls, you will have two end tetrahedral holes and one end octahedral. I hope that is clear. Now I want you to see the tetrahedral and octahedral hole in the FCC unit cell. We saw it in CCP. Let us see it in FCC. So in FCC, okay, I'll take you here, right. So your tetrahedral hole, okay, let me first tell you the octahedral hole. Octahedral hole lies at the body center as well as the edge centers. Okay, so how many octahedral holes are there? One at the center and the ones lying on the edge. So on the center of the edge. How many edges are there? 12. How much does one edge contribute to one cube? For example, this edge would be shared by 4 cubes. One here, one in the front, one on the top, one here, the top of the front one. Okay, that means each edge is contributing 1 by 4 to your cube, which means 12 edges will contribute 12 into 1 by 4, 3. That means you have 4 octahedral holes. The one in the body center because it is totally contributing to this cube and 3 coming from 12 edges. How many octahedral holes? 4. Okay. Now let's be a little smart and let's try to correlate whatever we just studied. How many lattice points are there in an FCC? 1 from the corner and 3 from the faces. 4. 4 lattice points. And I just told you that number of octahedral hole is equal to the number of the lattice point. 4 lattice point, 4 octahedral hole. Okay, so I hope you're good with me. Now, where does the tetrahedral hole situated? Okay, now what I do is I want you to open your imagination. Take this cube, cut it from here. Okay, XY plane. Now you have two rectangular cuboids. Now cut it along Z axis. Now you have 4, okay? And now you cut it along the XZ plane. So you will have 8 small cubes, 4 on the top, 4 on the bottom. center of each small cube is a tetrahedral hole. Okay, so I'll explain it once again. If you divide this cube into 8 small cubes, let's say you first cut it into half, you have 2, then you cut the top one into half, the bottom one into half, and then cut them again into 4 slices. You will get 8 small cubes. The center of each cube is a tetrahedral hole. So how many tetrahedral hole? 8. How many lattice point in FCC? 4. Number of tetrahedral hole are supposed to be twice the number of lattice point. That makes 4 and 8 fitting into this particular understanding that we just gathered. Okay. Now coming to a little more tricky thing, how to visualize tetrahedral and octahedral hole in hexagonal closed pattern. Right. Now for this, I would want to, because I was thinking maybe this would not be very clear, but okay, let's try to understand from here. Okay, this we just solved few slides back. The number of lattice points, forget about anion right now. Number of lattice points are 2 in the HCP, and we decided that the coordinates are 0, 0, 0 and 1 by 3, 2 by 3 half. Now, where are the octahedral hole? Okay, you consider this whole hexagon, and remember, only this is one unit cell. Okay, the one that goes down to the bottom, with this as a top face and this as the bottom face. Okay, the octahedral hole has to be surrounded by 6 atoms. So you consider these 3 top atoms. All right, and then you consider this middle atom lying in this unit cell itself. This is one at the back unit cell. This is one in the side. Okay, so you have this triangle, a staggered triangle. The center of this is your octahedral hole. Similarly, if you can imagine, now again we take these 3 and now we take this 3. Okay, so this is another octahedral hole. That means this unit cell that we considered has got 2 octahedral holes. How many lattice points were there? 2. Number of octahedral holes should be equal to 2. And that is what we established. Okay. Now, what are the coordinates? I'll tell you, I'll try to explain it to you. Maybe you'll have to, after the lecture, just spend 5 minutes on these coordinates again. Okay. So, the lattice point is 1 by 3, 2 by 3 half. Okay. But the octahedral hole is slightly shifted towards this because this is your octahedral hole. So the xy coordinates, if this was 1 by 3, 2 by 3, the xy coordinates are 2 by 3, 1 by 3. And the z coordinate, because this is 0, this is half, this is 1, this is 1 by 4, and this is 3 by 4. And they are lying right above each other. So once you have fixed the xy coordinate for 1, which is 2 by 3, 1 by 3, the second one is also fixed. Only the z coordinate changes 1 by 4, 3 by 4. Okay. So just take a minute, after the class, come back to this again, please. Otherwise, you will forget. Now let's try to look into tetrahedral hole, which is again, I would say a little more trickier, but I'm sure all of you are smart and we're going to solve it. Okay. Now again, this unit cell. All right. Now consider this triangle and the center atom which lies in this unit cell. So you can see this is a tetrahedra and this is a tetrahedral hole. Okay. One thing now that you have to imagine is just try to invert this tetrahedra. Okay. Okay, let me just do it. Now this is one tetrahedral hole. Now, if you can imagine in a tetrahedra, the center of gravity, that is a hole, will lie right below this particular tip. So the xy coordinate will be same as this atom, which is 1 by 3, 2 by 3. Okay. What about the z coordinate, right? In case of octahedra is a more symmetrical structure. The center of gravity or the hole lies exactly the half. So we had no problem. It was 1 by 4, this was 3 by 4. In case of tetrahedra, if this is the length of a tetrahedra, the center of gravity or the hole lies at actually, I would say 3/4 of this length. Like I'm talking of this length, and then 3/4 of this length. And okay, we'll come to deciding how to take the z coordinate in a while, but let me first show you all the tetrahedral hole. Now this unit cell has got two lattice points, so we have to find four tetrahedra somehow. Okay, so one is this, one is you again consider this atom and these three. Okay, this is the second tetrahedral hole. Now where is third? You consider this atom, all right, and this triangle in the center. This is third. Now again consider these three atoms and this atom. So there are four tetrahedra, two are pointing upwards, two are pointing downwards. Let us find out now what is the xy coordinate of the one that we just mentioned, that is these three and this atom, because it lies exactly on the cell edge. So its xy coordinates are 0, 0. Okay. And similarly, these three and this, it lies here. XY coordinate is 0, 0. Now we have to figure out the Z coordinate. For this, I tried to make this to make you understand. Okay. Now, let's say this was my 0, plane A, and this is my 1. Can I write? I want to divide it into 8 parts, just to make you understand. This is 0 by 8, and 1 can also be written as 8 by 8, 1, right? Now I divided into 8 equal parts, okay? And now I told you that the center of gravity of tetrahedra, if I measure the length of the tetrahedra from tip to the triangle, the center of gravity lies at 3/4 of that length. So if there is a tetrahedral hole like this, now consider these three atoms and consider this atom. Now it should lie at 3/4 of this length. That means because this plane is at half, okay? Now half into 3 by 4 is 3 by 8, all right? So now the coordinate of this becomes 0, 0, 3 by 8. I hope this is clear. Now moving on to this hole. Again, consider these three and the one at the top. Okay, now here the tip is here. So tetrahedral hole will be more towards this center layer. Again, 3 by 4. So you have divided into 4. So the z coordinate is now 5 by 8. 0, 0, 5 by. All right. Similarly, for this tetrahedra, it is 1 by 3, 2 by 3, 1 by 8. And this one, where you have these 3 points and this 3 will be 1 by 3, 2 by 3, 3 by. Little difficult to understand. We can discuss it again, but our request is to please go back and see if you can, kind of understand. If still you cannot understand, we'll come back to it. So I hope it is clear, and we'll again take a 2 minutes break, and then we'll come back to the common crystal structure. And let's hope if we can rush through them quickly, because now we have the concept of close packing, we have the concept of unit cells. Okay? Yeah. All right, any questions? You can type in the chat box. Are the things okay? Are you finding understanding these tetrahedral, octahedral holes a little difficult, or is it okay? Any response would be appreciated. Okay, thank you, Madhuri. The PPT might not be provided. I'm not really sure if they provide PPT, but I think the lectures would be available to you. And I'm sure you're able to see slides only on the lecture. So I think it should be fine. So I realize I've been told, and somebody has posted it also, that it's available in the Anuvidya website. So maybe when you log in, you'll be able to access them.
Microsoft PowerPoint.
Okay.
Share.
All right. So we are okay. So we are back to our lecture, and let's do some fun things. The concepts that we learned till now, let us apply them. All right. Okay. The first and the most famous structure in the solid state chemistry or for a materials chemist is rock salt structure. Why is it called rock salt structure? Because it is adopted by your common table salt that you use at home, which is sodium chloride, and also adopted by many more compounds like potassium chloride, silver chloride, then alkaline earth oxide like magnesium oxide, strontium oxide, etc. Okay. So what is the structure now? Now we'll try to see it in all the three ways. We'll try to see it as a unit cell. We'll try to see it as a closed packing. We'll also try to see it as how the polyhedra, they are linked together to get the structure. Okay. Now the rock salt structure, first of all, you can imagine it as a face-centered lattice of anions. Okay. So you make a unit cell with the anions at the face center. And when I say anions at the face center, lattice means make a cubic unit cell, put the anions at the corner and the face center position. Okay. Now, and then you keep cations in all the octahedral holes. Okay. Now that is an advantage to me because I already have taught you where the octahedral holes are. Octahedral holes are at the body center of the cube and the edge center. So black ones are your cations, which is Na plus. Pink ones are your anions, which are Cl minus. You know, now you can ask me, first let me tell you one important thing. Because this is NaCl, because the chemistry is 1:1, sorry, the stoichiometry is 1:1, also because, they adopt same kind of coordination number. Here, even if you had told me that, ma'am, I want to place Na plus at the corners and face center and Cl minus at the octahedral hole, I would have agreed with you because that would have created the same structure. But as we'll discuss further, this is not possible in all the cases. Okay, coming back to our structure, you have anions at the corner and face center position, cations occupying the octahedral voids. So 4 anions, 4 cations, 4:4, 4Na4Cl, your formula is retained, NaCl. That means every unit cell has got 4 units of NaCl in that. 4 formula units is what we call it. Okay. Now, again, you can ask me, here it was interchangeable, most of the time it will be not. Then, but I tell you, that try that you always make the unit cell or the cubic or the closed packing of anions and put cations in the void. Why is it so? Because your anions are bigger. The voids will be smaller. Cations are smaller, they would be able to occupy the void. That is why it is convention that we define the unit cell framework or the closed packing by anions and then cations occupying the relevant home. Okay. So this is how we define it in terms of unit cell. Another in closed packing, we say that chloride forms the cubic closed packing and Na plus occupy all the octahedral voids. Okay. Another way is I told you as a unit cell. Now, what are the coordinates? Now, once you have, if you listen to me in the previous few slides, now I don't need to tell you what are the coordinate of an ion, which is the coordinate of the lattice point, 0, 0, 0, and 3 lattice point on the faces. What are the coordinate of cations? The octahedral holes. What are the octahedral holes? The one at the body center is half, half, half. The ones at the edge center are 0, 0, half, half, 0, 0, 0, half, 0. Okay. What I want you to now visualize with me is I say that coordination number of sodium and chlorine is both 6. What is the coordination number first to start with? If you don't know what is a coordination number, it is how many number of atoms are surrounding the atom of my interest. Let's say if my atom of my interest is this sodium, which is at the bottom, body center, how many chloride are surrounding it? You count with me. 1, 2, 3, 4, 5, and 6. That means sodium is surrounded by an octahedra of the chloride. Now let us concentrate on any one chloride that you want to do. Now because we are not face to face, I can't ask for your choice. So let me choose this chlorine. Okay, the one at the face center. It has 1 sodium, 2 sodium, 3, 4, the one at the bottom and one in the top unit cell. So one chlorine is also surrounded by an octahedra of NaCl. Okay. Now, let me show you how are these related to each other. Can I express this in the form of polyhedra of chlorine and sodium? One thing that we have understood is I can describe my structure as formed of NaCl6 octahedra or ClNa6 octahedra, right? Now, how are these polyhedra or octahedra are joined together? Okay, now assume this was your chlorine. It is surrounded by 6 sodium. Now, imagine your this thing, this chlorine, all right, this chlorine. Now, it is surrounded by an octahedra where you have this edge and then you have this edge and the edge this, then this at the bottom, then this. So basically, if you realize this polyhedra is 1, 2 in the front, 3, 4, 5, 6, and this is one of the edge. So NaCl in terms of space sharing polyhedra can be described as either NaCl6 or ClNa6 octahedra sharing the edges. If you visualize it in terms of space filling polyhedra, this is how you will be able to see it. Okay. Now, calcium carbide. Why I took calcium carbide immediately after rock salt structure? This is your rock salt structure. Okay. If you are able to see it from the top, then this is one of the faces you will see. Or let's say front face that is facing you. Now here your anion is carbide, C2, 2 minus. Okay. Now let's say your cations are all these purple color, but your anion which was earlier spherical, the red color is now replaced by these elongated thing because carbide ion is elongated. Okay, so it adopts all the lattice point of the rock salt structure. But because one of the species, that is anion, is elongated, what happens is it becomes elongated in the C direction. So your A and B are equal, but your C becomes elongated and hence it adopts a tetragonal symmetry. Okay. The other important structure is sphalerite, which is also zinc blend. What is zinc blend? Zinc sulfide. ZnS. 1:1. Again. Okay. But here there is a little difference. Why? Again, your anions form the FCC unit cell, similar to NaCl, but now you have to place your cation in the tetrahedral holes. Okay, but let me remind you, or you remind me, how many tetrahedral holes were there in the cube? There were 8. The number of sulfide that you have put are only 4. So if you fill all the tetrahedral hole, it will become ZnS2. But my formula is ZnS. That means in the unit cell, only the alternate tetrahedral holes are filled. So if you are able to imagine those small 8 cubes, you will realize there are 4 tetrahedral holes on the top and 4 in the bottom. Out of this, you will fill only 2 and 2. So FCC of sulfide iron, zinc occupying alternate tetrahedral hole, 4 sulfide, 4 zinc, the formula is ZnS. The coordinates of anions are again like in the rock salt structure, but now the coordinate of your cations are changed, which is corresponding to the tetrahedral voids. And how do we define this structure in terms of polyhedra? If you try to visualize, this is your one tetrahedra. If this is a zinc at the center, this is 1, 2, 3, and 4. This is a tetrahedra. And here again, this is joined to this particular tetrahedral hole. So what you have is corner sharing, these two tetrahedra are sharing this one particular and this one corner. So ZnS structure can be described as ZnS4 or SZn4 tetrahedra sharing corners and then propagating in 3 dimensions. Okay. Now you ask me, NaCl also has 1:1, zinc sulfide also has 1:1. Then why did you tell us that वहाँ पे they will occupy octahedral hole and यहाँ पे they will occupy only alternate tetrahedral hole? Why should it be like that? What decides whether an AB compound having the stoichiometry 1:1 will go to rock salt or it will go to zinc blend? Okay? Even though if you do not have any experience, for you it is difficult to understand, but there are certain guidelines. So rock salt structure is favored by more ionic compound and zinc blend is favored by relatively covalent compound. Okay, so because it is favored by more ionic compound, it is favored by oxide. Chalcogenides are sulfide, selenide. Chalcogens is group 16 of alkaline earth metal and metal halides. And these are chalcogenides of relatively either the smaller ion or the transition metal ion because they cannot give and take electrons, so they form more covalent bond. Now, a reason for, if you tell me, why should NaCl be favored by more ionic compound? See, ionic compound are held together by electrostatic attraction. Okay. More is the attraction, more stable is the structure. So more is the number of anions around each cation or vice versa. More will be the pairs that are having electrostatic attraction. So that is why ionic solid tend to form the structure which have higher coordination number. Now, if you were with me in last 2 slides, you will realize in rock salt, the coordination number was 6 Na by 6 Cl, 6 Cl by 6 Na. But in case of zinc blend, your zinc was in tetrahedral hole. The coordination number was 4. Similarly, sulfide, if you are able to imagine, the one it is in the corner, it has 1 zinc here, 1 zinc at the back, 1 zinc on top here, 1 zinc on top. So the coordination number is 4:4. Okay. Covalent compound prefer lesser coordination number, ionic compound prefer higher coordination number, and that is how Compounds having stoichiometry of 1:1. If they are ionic, they will prefer rock salt. If they are covalent, they will prefer more zinc blend kind of structure. The second structure that I talk about is cesium chloride. Okay. Now, cesium falls in the same group in periodic table as sodium. Okay. But with sodium, with sodium and chlorine, it forms a rock salt. Cesium and chlorine, it forms the primitive structure. Okay. How do I define it? So your cesium or chlorine, take any one of you, I'll give you the option, occupying the corner of the cube. Whereas the other thing, let's say chlorine was occupying, let's go by convention, put anions at the corner, the cesium will occupy the body center. Okay. Now ask me the question, if we were sitting here face to face, if this atom is occupying body center, why are you not calling it body center, but you are calling it primitive? Primitive means only one lattice point. Body center has two lattice points. Why are you calling it primitive? That is because we call a unit cell body center or face center or end center only if the atom that is present at the centered position, either it is body or face or edge, uh, is same as the one that is occupying corner. Then only we call it a centered lattice. If the atom that is present in the body center is different from the ones that is present at the corner, or the atoms that are present at the face center is different from the ones that are present at the corner, it is a primitive lattice. Because for one particular atom, you still have one lattice point in this unit cell. Okay? Very clear. Coordinates of anion is 0, 0, 0. Coordinate of cation is half, half, half. Or vice versa. If you didn't feel like putting anion at the corner and you want to place only cation at the corner, you're very welcome. In that case, the coordinates would interchange. Now, what is the coordination number? Concentrate on this atom at the center. It is surrounded by 8 different atoms. If you concentrate on this corner white atom, you can easily imagine it will have 8 red atoms. One at the back, one here, and then 4 cubes in each of the 4 cube on this side. Okay. So coordination number of both cesium and chlorine is 8. Now I want you to ask me the question, why is that NaCl was rock salt? Why is that cesium chloride is? Even though cesium chloride is also ionic. There we could differentiate ionic and covalent. What is your reason here? It adopted rock salt. This one adopted primitive. Okay, the reason is because it depends upon the relative sizes of the ion. Okay, now cesium and chlorine, their radius ratio, we'll talk about radius ratio in next class. Their radius ratio is such that a cesium can take 8 chlorine around it, while a sodium cannot. Okay, an ionic solid, if they will prefer always as high coordination number as possible. Because it can take 8, it will give more electrostatic interaction, it will give more stability, so it will not go to rock salt. It will, because in rock salt the coordination number was 6. Okay, so that is how, these are not hard and fast, but these are the general guidelines by which we can understand the crystal chemistry or why a certain compound adopts a particular structure. Okay. Now, this was till now it was all AX structure or AB structure. NaCl, ZNS, CHCl. What if I change the stoichiometry to 1:2? That is AX2 structures. Now, first one is anti-fluoride structure. Okay. Now, anti-fluoride means nothing based on your zinc sulfide. The only difference here is, okay, now, no difference here. Zinc sulfide lattice means place your anions, which are the blue color oxygen, at the face centered position. It means corner and the center of the faces. And in zinc sulfide, if you remember, you had filled alternate tetrahedral. Now be lavish, take your chances and fill all the tetrahedral holes with sodium. What you get is Na2O. Why Na2O? How many blue lattice point will you have? 4. It is FCC. How many tetrahedral holes you have? 8. 8 sodium are occupying it. So 8 sodium, 4 oxygen, Na2O. Okay. Now, till now, if you remember, NaCl, Na had the coordination number of 6, Cl had the coordination number of 6. ZnS both had the coordination number of 4. CSCl both had a coordination number of 8. But here the story changes. Now because the stoichiometry is different, then coordination numbers are different. So let us figure out what is the coordination number of Na and oxygen. Okay, now it is easy to understand. You are placing Na in the tetrahedral hole, right? So coordination number of Na has to be 4. It is surrounded by 4 oxygen, right? How? And the coordination number of oxygen, but now is 8. It is surrounded by 8 sodiums. How? If you consider this corner blue oxygen, this is 1 sodium. Then there will be sodium at the back. There will be sodium in the top cube. There will be sodium in the side cube. Similarly, there will be 4 cubes on this side. So it will be surrounded by 8 sodiums. All right. So coordination number of sodium is 4, oxygen is 8. And in terms of space filling octahedra, now earlier NaCl6, ClNa6, you could describe it in terms of any of them, but they would be sharing edges. But here, if you want to describe it as NaO4 tetrahedra, it is edge sharing NaO4 or corner sharing cubes of ONa8. Okay, a little difficult to visualize here, but this is how it is. All right. Now this was anti-fluoride. What is fluoride? No complication. Just reverse your anion and cation. Why? Because here the formula was Na2O. So whatever is 2, that goes into the tetrahedral interstices. In fluoride structure, your anion is twice. Plus, till now we were keeping anions at the corners and lattice positions because they are bigger. Now fluoride is smaller as compared to calcium 2+. So calcium forms the FCC lattice and fluoride occupies all the tetrahedral holes. Everything else remains like Na2O. Okay. Now coming back to this was, now till now whatever structures we did, rock salt, zinc blend, cesium fluoride, anti-fluoride, fluoride, these are the backbones of crystal chemistry. But these structures were based on cubic close packing. Okay, that is why your unit cell was FCC all the time. Now we move to the regime where you have structure of AH type, but now your close packing is hexagon. Okay, so the first one is nickel arsenide, and mind you, even nickel arsenide has 1:1 like NaCl. But here, there I told you, it is your wish. You place fluoride at the corner or Na at the corner. But here you will have to be very careful to place only anion at the corner because the atom that goes at the corner will have different polyhedral arrangements. Sorry,
Hello, ma'am.
but now the arrangement will be different. Okay. So how is it different? In nickel arsenide, what we say is that your arsenic ion is the blue ion. It occupies all the corner position in the hexagonal cell. And the nickel, it occupies the octahedral hole. So 1:1, 2 lattice point, 2 octahedral hole, 1:1. But what is the difference here? The polyhedra of nickel, now nickel is lying in an octahedral hole, right? So it is like this. The green one is nickel. So the arsenic are arranged as octahedra. That is, I showed you that octahedra can be represented by 2 triangle also. So 2 staggered triangle. But when you consider the coordination polyhedra of arsenic, still 6 nickel. The coordination number is still 6. But now rather than staggered triangle, they are arranged as eclipse triangle. Here, these nickels are lying directly above each other. So whatever arsenic comes in between, it is actually seeing nickel as 2 eclipse triangle. That is triangle exactly are lattice, that nickels are exactly over one another. Okay, and this arrangement is called trigonal prism. It is a face of triangle and it is in a form of prism. So the coordination number of both nickel and arsenic are 6:6, but the polyhedra of nickel is octahedral, polyhedra of arsenic is trigonal prismatic. Coming to what we call as Woodside Woodside is again zinc sulfide. It is a different polymorph. See, the zinc sulfide can occur as zinc blend, which we studied earlier, having cubic closed packing tetrahedral hole. Now, Woodside is also ZNS, but here you have hexagonal closed packing, again sulfide occupying half the tetrahedral hole, but the closed packing is now hexagon. Okay, so this is how it looks like. The coordination number is all tetrahedra. There is no change in the coordination number of the, coordination polyhedra of the cation and anion. Now I will talk about slightly different structure. You know, everything in the word, if it was ideal, the word would have been really beautiful. Okay. If CCP was all CCP, all naturally, all nicely ordered, HCP was all HCP, it would have been really fun, easy to understand. But nature doesn't exist like that. So we have certain structures which are built on CCP and HCP, but they're slightly distorted. Distorted means bond lengths won't be equal, the polyhedra would be tilted or something like that. So the first among that is a very famous compound called titanium dioxide. It is present in your cosmetics, it is present as a antibacterial layer on your fridge and all that. A very common mineral. What is its structure? It has a hexagonal close packing of oxygen, but that is distorted. Okay, it's not regular. And titanium occupies octahedral hole, but because titanium is half the number of oxygen, so it is clear to understand that it occupies half the octahedral sites. Because the number of octahedral sites will be equal to the number of oxygen, and oxygen is double, so titanium occupies half the octahedral site. But how are those half octahedral sites are occupied? Okay, if you remember, let me take you here because I kind of made some simpler this thing for you. These are your octahedral holes. If you remember, they lie one above one above other, and they also lie this way. So I will call these as layers and these as rows. So in case of titanium dioxide, alternate rows are occupied. Okay. And when it is not occupied, you will not see it as an octahedra, right? You will see it as an empty space. So it somehow looks like that you have edge sharing titanium O6 octahedra. These are infinite chain and parallel to C axis, and along AB they share corners. Okay. Now I would want to spend a minute here to show you. Many of you might not encounter it, but it took me a little while to understand. So just to make it easy for you, how do you see this is an octahedra? Okay, so this is your square. This is how crystal chemists they represent in two dimension. This is your square. This atom is at the bottom, and there will be an atom on the other side. Okay, so that is how you look at the octahedra. So I hope this is somewhat clear because I'll repeat it fast. Distorted HCP of oxygen, titanium occupying half the octahedral side, and alternate rows are occupied so that you have edge shared TiO6 along the C axis, and they are linked by with corner to the along the AB axis to form a 3D network. Okay. Another interesting thing, CDI2. Same configuration as TiO2, 1:2. Again, outside from HCP, cadmium occupies half the octahedral site, but here the story changes, Cadmium also occupies half as titanium, but rather than occupying the octahedral site in the row, it occupies in the layer. Okay, so what happens is one layer of octahedral, these are the iodide layer in HCP. This is cadmium occupying one layer, another layer is empty. Cadmium occupying, say, third layer, another layer is empty. Now, what is the implication of this? I just told you that in the beginning of the class, that crystal structure defines your property. CDI2, because of the fact, when I say nothing is present, this octahedral hole is not occupied, means nothing is here, right? So CDI2 forms a layered structure, and these layers, the one which are occupied, they are held together by van der Waals forces in between. So actually, these layers can slide over each other. And the fact that they're empty spaces make these kind of structures very important as ion exchanger or something wherein these spaces can, some ions can come and go through these spaces, leading to widely different properties. Okay. Repeating it fast, CDI2, HCP of iodide, half the octahedral holes are occupied, but now alternate rows are occupied by cadmium. CdCl2, because it is CdCl bond is more ionic as compared to CdI bond. Again, a difference. More ionic compound tend to form CCP, lesser ionic tend to form hexagon nucleus pattern. So CdCl2 forms CCP of chloride, not HCP, and cadmium occupies half the octahedral side. Similarly, alternate layers are occupied. Okay. So this is it for this class. We have come to end of it. Silicate structure we'll do only if we feel like, otherwise we'll come to it to the silicate structure at the end of the next class, because there are more important things that I would want to discuss. And towards the end, I also get a little tired. You also, I assume 1.5 hour lecture is not very easy to sustain your interest. So this is what we'll do. Okay. I hope whatever we did today was clear. We talked about octahedral holes. We talked about, I'm sorry, it is gone. Wait. Okay, we talked about different crystal structures, CCP, HCP, some common crystal structures, how the polyhedra are linked together. And I hope it was, if not completely, but a major part of it was understandable to you. I'll stay on for 2 minutes if there's anything that you would specifically like to ask or make a comment upon. And as I mentioned in the last class, you're most welcome to communicate with me through HPNI. You can send the questions to them, or you can also send the questions to my mail ID. I'd be very happy to answer it to you. If I don't know, I'll work on it and get back to you. Okay, so going to the chat box, and if there's anything that you would want to ask or comment, you are most welcome. All right, if nothing, then thank you very much for your attention, and I'll meet you on Friday, okay, at 2:30. Thank you.
Hello.